Our project for the software designed to empower underserved populations capstone is the Vaccine Impact Modeling Tool, an interactive modeling tool which, given user input, models pandemic outcomes and displays them on a global map. When COVID-19 vaccines were approved, a natural question that arose was the best way to distribute vaccines to lessen severe pandemic outcomes. Although tools exist to display models or up-to-date COVID data, few tools incorporate both. Our goal was to design such a tool. The overall system is composed of 4 key components separated across the front end and back end. The front end is composed of a visualization tool that has an interactive map and parameter tuning panes. The back end is composed of a central server that serves client requests for web resources and model output, a data aggregation and parsing tool that compiles vaccination data daily, and a modeling engine that generates output given certain parameters. Created using the JavaScript E3 library, our visualization allows a user to view modeled data. A user begins by modifying parameters, either globally or for individual countries. If default is chosen in the global parameters pane, then values provided from either the data aggregator or configuration file are defaulted to. Otherwise, it will consider every country to have the value input by the user. Parameters for individual countries can also be modified. At this point, the user can click Simulate, which will run the model. They can use sliders to change the time they are viewing, and drop-downs to affect which populations are visible on the choropath map, with darker colors meaning more people are in that category with relation to the entire country's population. When a user clicks on a country, a pop-up window built with the library chart.js allows user-friendly graphs. A user can see the trend over time for that country and view the trend line for specific populations. Data is retrieved daily from the Our World in Data project and John Snow Labs using HTTP requests. This raw data is parsed and cleaned to produce parameters needed for the model and the visualization, such as the population data for each country, the daily average for vaccinations for the last 7 days, and the virus-induced mortality rate. Our project uses a custom SEIR model written in Python. An individual is considered as being part of one of 6 states: susceptible, exposed, infectious, recovered, dead, or vaccinated. Parameters such as the reproduction number, the average number of days spent in the exposed and infectious stages, and the virus-induced mortality rate affect how people move between categories. When vaccination begins, the portion of the population the user has specified as willing and able to be vaccinated become vaccinated at the provided rate per day. Vaccinated individuals are less likely to become infected as specified by the vaccine efficacy. We didn't want our project to be hard-coded for a specific model. A modeler can write their own model in Python and specify what parameters they want it to take in the configuration file. The data workflow is as follows. Once daily, the data scraper fetches data. The parser formats the data, patches holes, adds modeler-specific variables and default values for each country based on a configuration file, and places this into a master JSON file, which is saved in a data store on the central server. Once daily, the default model output is updated with the new master JSON file. When a user makes a connection to the web page, all of the page contents are returned by the central server. Additionally, a copy of the master JSON file and default model output is served to the front end. The front end displays the default data and maintains a copy of the default parameters in the master JSON. The user tunes parameters as needed and clicks Simulate. The customized parameters are sent as a post request to the central server. The central server parses the JSON and calls the modeling function. The model simulates the pandemic for the given number of days using the given parameters for each country and returns the results. The central server returns the model results to the front end, and the front end displays the new model output. Through models, data scraping online data sources, server-side post and GET requests, and JavaScript HTML visualizations, we were able to create a tool that effectively allows public health officials to make informed decisions about COVID-19 vaccinations. We're hopeful that this tool can be used as a building block for future work in this field, and improvements can be made to really make an impact on COVID and future viruses to come.